I now call to order the Society's 2,462nd meeting in what is now the 151st year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW Science, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends, including everyone here in the Powell Auditorium, at the Cosmos Club, and everyone tuning in on Zoom and on YouTube to tonight's lecture by Ralph McNutt. The Society is grateful to the sponsors of the 2022-2023 lecture series for their support. The Policy Studies Organization, in cooperation with the American Public University, and a generous donor who has asked to remain anonymous. Tonight is the Society's annual meeting, and the annual report on the state of the Society is to be delivered. First, the report of the Audit Committee. The committee met a few weeks ago. The finances were audited and found to be sound and without objection. A copy of the Audit Committee report and a financial report are available by request to the corresponding secretary, correspondingsec@pswscience.org. I am pleased to report that the Society was able to hold 9 meetings in person and another 7 via Zoom during the fiscal year ending June 30th, 2021. Member support was strong, about the same as the previous year in terms of membership. Financial support in the form of dues, additional contributions, and sponsorships also was strong. Income again exceeded expenses. The surplus was augmented by the low cost of Zoom-mediated meetings. Reserves remain adequate. New member applications were about the same as last year and remain substantially below pre-COVID levels, however. Attendance at the in-person events was mixed. Average attendance at the receptions and dinners returned very nearly to pre-pandemic levels, but attendance at the lectures themselves remained depressed. On a hopeful note, there was a steady increase in the lecture attendance toward the end of the spring lecture series. We added a Zoom webinar to the in-person meetings alongside the live stream to YouTube to afford members a way to ask questions directly via their computer microphones. Participation via the webinar added to the overall audience. The Society posted edited recordings of all meetings to the PSW website and to the PSW Vimeo and YouTube channels. There are now 183 videos in 15 playlists. Video viewership of newly posted videos on the YouTube channel averages several hundred in the first 2 weeks after posting. Collectively, the videos have been viewed approximately 600,000 times. The Society is looking forward to continued growth in the coming year, increasing its capacity to utilize projective and participatory technologies like Zoom, and to add some new programming initiatives. In short, the Society has come through the pandemic in good financial health with a strong membership base, but contemporary viewership is not yet back to pre-pandemic levels. So we're looking forward to strong and interesting programs and to further revitalization and real growth in the coming year. If anybody has any questions about the state of the Society, they can please address them to me via email, president@pswscience.org. I'm pleased to announce the following new members. Sandeep Kalsi, Program Manager, ASRC Federal, interested in planetary science, AI, and science and politics, who learned a PSW from Shahid Aslam at NASA. Brandy Svensson, Security Analyst, European Central Asia, with the World Bank Group, interested in the environment, green technology, and health sciences, who learned a PSW from PSW member Cameos Lance. Sean O'Donnell, President at RAD5 Health Strategies, interested in biotechnology, neuroscience, and astrophysics, who learned a PSW from Mark Heller. Dennis Willey, Army Space Operations Officer, interested in a wide range of space-related topics, who learned a PSW from PSW member cameo lens. Tarek Al-Harari, architect project manager with Georgetown Design Group, whose recent project was restoring the Hungarian embassy building. Interested in material science and space, who learned a PSW from a friend. John Philip Dowling, retired from NASA after a long career at the NASA Goddard Space Flight Center, interested in nuclear physics, orbital mechanics, and spacecraft trajectory design, who learned a PSW from PSW member and former President Joe Foreman. And tonight's speaker, Ralph McNutt, who learned a PSW from our invitation to him to speak tonight and from PSW member Casey Liss, whose interest will be clear in part from tonight's lecture. We welcome them to membership. If you are not a member and would like to join PSW or support the Society, you can do so through the PSW website using the blue Join button on the upper right-hand corner of the homepage. We welcome new members and appreciate donations. All new members are entitled to a copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, covering the period from March 11th, 1871 to June 1874, in which you will find an explanation of why the society was founded, why it was named, what it is named, and who founded it, as well as such interesting articles as how to calculate the value of pi to 30 decimal places. If you are a new member and you have not yet gotten your copy, please see me after the lecture, and I will be glad to hand you one signed personally by me on behalf of the membership. All members are entitled to wear the PSW Science Rosette. The results are $15 plus 90 cents DC sales tax. They can be purchased online or at the Rosette table in the back. But please note, Rosettes must be picked up at a lecture in the Cosmos Club. Generally, PSW cannot mail them to you because tax accounting complexities are onerous. Sales taxes are levied based on the recipient's address, and we're not going to get into the business of figuring out what sales tax we owe in 50 states of the Union. Write your congressperson. Member at Large Social Media Director Ann McQueen will now read the minutes of the 2,461st meeting and the lecture by Sobita Satyapal on supermassive black holes, prepared by Recording Secretary James Hewlin, who is currently in Salt Lake City.
Thank you, Larry, and good evening, everyone. On June 17th, 2022, from the Powell Auditorium of the Cosmos Club in Washington, D.C., and streaming online via Zoom and the PSW Science YouTube channel, President Larry Milstein called the 2,461st meeting of the Society to order at 8:08 p.m. He announced the order of business and welcomed new members. The recording secretary then read the minutes of the previous meeting. President Milstein introduced the speaker for the evening, Sobita Satyapal, professor of physics and astronomy at George Mason University. Her lecture was titled Supermassive Black Holes at the Centers of Galaxies: Accretion, Dynamical Interactions, Galaxy Evolution, and Cosmic History. Roughly 26,000 light years from Earth lies the center of the Milky Way. Because space dust prevents visible light observation, the center of the galaxy was only first seen in infrared and revealed a dense cluster of stars in that area unlike anywhere else in the galaxy. Scientists have since observed the orbits of stars that form that cluster and calculated the mass of the dark object at the galaxy center to be approximately 4 million times the mass of our sun. Most recently, a group from the United States and Germany shared a Nobel Prize for imaging the dark object and providing irrefutable evidence that it is a supermassive black hole. The Milky Way's supermassive black hole is not unique. One has been identified in a nearby galaxy, M87, and the Sloan Digital Sky Survey has generated data suggesting that supermassive black holes are at the center of every massive galaxy the survey has observed. The size of the black hole appears to correlate with the stellar mass of the galaxy in which it resides. That correlation suggests black holes play a role in shaping the evolution of the resident galaxies. Satyapal then addressed how supermassive black holes form. Typical black hole formation is well understood to occur where the stellar remnant of a supernova is massive enough that it collapses into a singularity. Satyapal's research focuses on how black holes grow into supermassive sizes of more than 1 million solar masses. In the 1950s and the 1960s, scientists began identifying quasars, which are extremely active or feeding supermassive black holes in high redshift. Quasars formed in the early universe, and their existence challenges classic black hole formation history and theory. The speaker then described various theories put forward to explain the origins of supermassive black holes. One theory, called POP3, is that supermassive black holes are the end products of the most massive stars in the early universe. For this theory to work, black holes would need rapid and continuous accretion to become supermassive. Other theories are that the conditions of the early universe were just right for supermassive black holes to form directly from gas clouds or stellar clusters. The speaker discussed the challenges posed by each formation theory. She predicts a breakthrough within the next decade. Satyapal then presented her argument for how observing low-mass galaxies, or dwarf galaxies in our local universe, can tell the story of supermassive black hole formation in high redshift. Dwarf galaxies may mimic the seeds of young black holes before they grew to supermassive size. If the POP3 model is accurate, the speaker expects dwarf galaxies to contain a significant fraction of low-mass black holes. But if supermassive black holes are formed from gas clouds, the number of black holes in dwarf galaxies should be fewer. The speaker believes observing local dwarf galaxies will provide data to resolve this question. At this point in development, future supermassive black holes at the centers of dwarf galaxies should be accreting intermediate black holes. These intermediate black holes are difficult to confirm because they lack the angular resolution for scientists to measure their gravitational influence. Satyapal's team instead focused on optical spectra that they believe represent accretion disks ionizing surrounding gas. The speaker then highlighted the work her group, Jenna Can, now at NASA Goddard, determined that accretion disk temperature and peak wavelength emission depend on black hole mass. More energy is emitted in shorter wavelengths, as confirmed by the observations at the Keck and Gemini observatories. If accurate, this determination will give scientists a tool to distinguish between supermassive and intermediate black holes. Satyapal's team has time in the next year on the James Webb Space Telescope to confirm this hypothesis. The speaker then discussed theories for how supermassive black holes grow to such massive sizes. One theory is merging galaxies feed growth. Such mergers are common and simulations support this theory, but observational data indicates mergers involving active galactic nuclei are rare, with fewer than 30 dual active galactic nuclei mergers known in the entire universe. Because most active galactic nuclei observations have been optical, Satyapal's group has been searching in the infrared and X-ray and are identifying previously overlooked candidates. She is optimistic that searching for active galactic nuclei beyond the visible spectrum and with advanced instruments such as the James Webb Space Telescope will reveal data to support the merging galaxies growth theory. The speaker then answered questions from the in-person and online viewing audiences. An in-person member asked, if funding were not an issue, what kind of data would the speaker like to obtain to explain how supermassive black holes grow? The speaker said direct supermassive black hole mass observations would be definitive. A Zoom viewer asked how scientists can confirm POP3 quasars contain heavier elements that are indicative of supernovae. The speaker said those stars should be primarily composed of hydrogen and helium and metal poor. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:57 p.m., President Milstein adjourned the meeting. Temperature in Washington, D.C., 32 degrees Celsius. Weather, mostly sunny. Attending in person, 44. Concurrent live stream viewers, 48. Number of online viewers in the first 2 weeks of posting, 177. Respectfully submitted, Anne McQueen on behalf of the recording secretary.
Thank you, Ann. Appreciate your standing in for James. Are there any questions, comments, corrections to the minutes? Hearing none, do I have a motion to accept the minutes as read? Do I have a second? Okay, the minutes are accepted as read and will be posted to the website in due course. We now turn to tonight's speaker, Ralph McNutt, and his lecture on a first interstellar probe, next step to the stars. Ralph is a physicist and member of the principal professional staff at the Space Exploration Sector of the Johns Hopkins Applied Physics Laboratory, fondly known as APL. And he is the principal investigator on the Pragmatic Interstellar Probe proposal. Concurrently, he is a co-investigator on NASA's Voyager, New Horizons, and Parker Solar Probe missions, currently operating, and on NASA's Europa Clipper mission, now under development. Ralph is an author on over 220 papers. He co-chaired National Academy's 2009 studies on radioisotope power systems and NASA's 2017 Large Strategic Science Missions. Among other honors and awards, Ralph is a member and trustee of the International Academy of Astronautics. He is a recipient of the APL Lifetime Publication Award, the NASA Silver Achievement Medal to the Parker Solar Probe team, the IAA Laurels for Team Achievement Awards for the Parker Solar Probe, New Horizons, and Messenger missions, and he is the recipient of 13 NASA Group Achievement Awards. Planet 172191, Ralph McNutt, is named for Ralph. Ralph earned his BS in physics at Texas A&M and his PhD in physics at MIT. All questions will be fielded after the lecture during the Q&A session. Ralph, the stage is yours.
Great. Thank you so much, Larry. Well, it is a real privilege to be here tonight, and thank you all for coming. And what I want to do is to basically tell you a story, and it's a story of an intersection between science and engineering, and some dreams that a lot of us have about maybe what we might be able to do in the future. So overall, this study is something that's been going on for 4 years. It's now come to a close. There have been contributions from a lot of people. We've counted about 500 people from around the world that have been involved with some phase of this, at least taking a look at it. There's a study report that's been completed with 190 people who've contributed to that. Some of the people that contributed are actually here in the audience tonight. 146 talks at over 46 events. I don't think that includes COSPAR because I didn't have a chance. It happened last July because I haven't had a chance to put that in yet. And about 51 white papers to various studies done by the national academies. So this really has been a science community effort, and a large one at that. So let me start out with the question of, well, okay, so what is an interstellar probe? So this gets bandied about a lot. Well, the pragmatic one, and I'll say some more about pragmatic as we go through the talk, it's a mission through the outer heliosphere into the nearby local interstellar medium. We're not going to Alpha Centauri or any place else, but we are going to be going on into the area beyond where the sun lives and where we live to find out more about how our home in the galaxy actually affects us. So, and the idea of it being pragmatic is to use today's technology in order to do this. And I'll say a little bit more about that. And the idea is to be able to do something that is faster than and farther than the Voyagers, which are currently the most distant things that are out there that we've ever built. And but we're sort of accidental visitors to the local interstellar medium. It's a region of space they were never really built to visit back when they were launched back in the 1970s. And the idea is also that this would not necessarily be the one and only. This would be a path maker for other things to come. So this whole idea about journeying out into interstellar space has basically been framed as being a 50-year journey by design. Voyagers have now been out there for 45 years, and that was definitely not by design. They were designed to last for 4.5 years. And a lot of good engineering and a little bit of luck has enabled us to be able to get where we have with them. And the idea also is that by design, what we would do with this in order to enable a solid 50-year productive lifetime is to have every decade to turn over the engineers and the scientists and the managers that would be in charge of the mission and really do something that hasn't been done before at NASA, at least not by design and up front, in order to be able to maximize the amount of information that we could get back from the mission and the amount of science that we could get. So this study is something that was commissioned by NASA to the Johns Hopkins Applied Physics Laboratory. This is in 2 phases. The Interstellar Probe, as I'll show, is not something that's new by any means. But we were asked to restudy the mission. We're starting now with the Solar and Space Physics Decadal Survey by the National Academies. That's starting up. Back when we were talked to by NASA about doing this was before that had started. This goes back to 2017. Some of the discussions began and into 2018. But the idea was to be able to prepare for the decadal, to at least have some input, some good technical input to that study team of this mission that has been talked about for a long, long time. And overall, the second part of the study was then done with a deep dive into the engineering, and I'll talk about some of those results. And that was over at the end of April of this year. There's a 498-page mission report, which can be downloaded from the web, and you can read it in your spare time if you'd like. There's also an executive summary that really sums up the mission that is also out there. And again, all of this is input for the decadal, which has just started deliberations now. Sort of by the numbers, this was a $7 million engineering study. So it was enough money to be able to actually take a really close look at what one could and couldn't do. This is about the same scope of the engineering study that was done by APL for what turned into Parker Solar Probe, going back to 2001 to 2004, which is when the notion of that mission started. And of course, it did not launch until 2018 and is being incredibly scientifically productive even now. We've had a huge number of volunteers that have been working on this. Most of the scientific pieces that have been worked on have been from volunteers. And again, I mentioned the 190 authors and co-authors. Again, a lot of voluntary input. And we've also done 16 webinars. Each of those are about 60 minutes each, and those are all published on the web. So again, giving some input about some of the thoughts as we were going through putting the study together. So I'm going to back up a lot and talk a little bit about initial thoughts. And again, this is this kind of motivating question of where did things come from. So we're going to back up to the 19th century. And most of you probably have heard of Jules Verne and H.G. Wells. And actually, these were the people who really started up what turned into the field of astronautics, if you go back through the records. And actually, Verne, of course, was older and was one who inspired Wells, who also came up with his own contributions with the War of the Worlds. There's something called the technology readiness level, which is a way of looking at the various levels of technology you need to put into a mission. It usually starts with a TRL of 1 with the first ideas. I've put these guys at TRL of 0 because this is sort of a precursor to those first technical ideas in order to kick things off. You need knowledge as well. And it's an interesting piece that actually Pierre and Marie Curie actually play a role in this as well because of their discovery of polonium and radium back at the beginning of the 20th century, who again were motivating factors in a lot of the thoughts at the time, which was feeding into really the founders of astronautics, all the way from Konstantin Tsiolkovsky to Hermann Oberth. And of those, 2 thought about the idea of traveling to other stars. One was Konstantin Tsiolkovsky. Of course, the rocket equation is something that he derived. And then, of course, Robert Goddard was the inventor of the liquid-fueled rocket, which he flew from his Aunt Effie's cabbage patch in the 1920s in Massachusetts. Both of them were thinking about what could you do to be able to get to the far distances as far as other stars. Tsiolkovsky had talked about in his investigation about our spaces by rocket devices. That was published in Moscow in 1911. And he talked about the idea of drawing upon these new radioactive substances that had been discovered as a means perhaps of getting into ultimate rocket propulsion. Similarly, Goddard was speculating on, well, what were we going to do when the sun burned out? And oh my God, we're going to have to do something about maybe trying to get the human race to someplace else. And again, he drew upon this idea that maybe there was something in this new kind of atomic energy that might be able to be a motivating factor in order to be able to do something with rockets. So anyway, these sort of set some of the background and some of the thoughts that people had had early on about what one might or might not be able to do. Fast forward to the modern world of space missions. So, my claim is that you've got to have 4 elements for any successful mission, any mission at all that you're going to do. You need to make a case for going. That's a combination of science and politics. And for those of you who think that there is no politics, well, I can give you some references. The means to go, technology. Okay, so the engineering side of the house likes to focus on the technology. The science side of the house likes to focus on the science, and they think about the politics as well. But you also have to have agreement to go. You've got a lot of stakeholders that are involved in any of these large missions. And that's really a question of strategy, and then you need to have the funds in place, and that's policy. You have to have, you'd have to have really deep pockets indeed to be able to fund something like this. And indeed, if you look back at all of the missions, the robotic missions that NASA has been doing, going back to the late 60s, over something like 60 years, the U.S. has spent something like about $79 billion in funding robotic space exploration. Thank you to all the taxpayers out there in the audience. But you need all of these people, you need all of these things to come together. And if you look back at the historic record, it has always taken all of these things to come together to make things work. And that's because, as another inventor said, vision without execution is hallucination. And one can argue that there are a lot of people that hallucinate in this field as well. And one of the things that we are trying to do in doing this study is to try to steer clear of that. So the real beginnings on Interstellar Probe actually go back to the beginning of the space program, the beginning of NASA. This is actually from a report in March 1960, the so-called Simpson Committee report from the National Academies. There were a variety of missions that people were looking at, thinking about the quote-unquote far future. There were 3 things that were identified by the people on this committee. John Simpson was one, Jim Van Allen was another. Again, people that were involved with space at the time and really trying to think forward about what we could do with this new capability that we had from rockets. And the idea that one of them was to do an outer solar system probe and basically to launch something in the plane of the ecliptic to go as far and as fast as possible away from the sun. And again, these are scientists, and they said, well, you know, by 1965, maybe about 5 to 6 AU per year as a speed might be something that's easily achievable. And of course, we're not there yet. I'm going to say a lot about, I'm going to use the term AU a lot. AU, of course, 1 AU is an astronomical unit. It's the mean distance between the Earth and the Sun. So if you're an American, it's about 93 million miles, and if you're anyone else, it's 147 million kilometers. I'll tend to use kilometers, because that's what NASA does. So that really set the wheels in motion about people thinking about such a mission. From 1960, by 1965, it turns out that Gene Parker, for whom the Parker Solar Probe is named, actually was thinking about this kind of a mission as well. Of course, the Voyagers were launched in 1977. Before that, Pioneer 10 and 11 had been launched, going out to Jupiter and Saturn, and then escaping from the solar system in 1972 and 1973. There were studies done by NASA in 1990, a large JPL study in 1999. There had actually been a precursor JPL study done, the Jet Propulsion Laboratory, of course, in Pasadena, California, in 1976, 1977. I'll say a little bit more about that. A variety of other studies, including the Keck Institute for Space Studies, a couple of studies that were done in 2014 and 2015. And that was about the time that we started thinking about this mission at APL, really being motivated by this new interest that a lot of people in the community had expressed in trying to do something like this. Now, the science questions really are not new. That's one of the things about this. They've really been enduring over all these years. They have not been changing around. It's always been a question of, well, we know the questions are there, we still want to answer them, and we're trying to figure out how in the world do we go about doing that. So this study was done on the eve of Voyager. There were primary objectives with respect to the sun's home in the so-called heliosphere. a term coined by Alex Dessler in 1967 to include the region of space that was dominated by the supersonic solar wind. That was something that Parker had predicted and then was confirmed by the instrumentation on board Mariner 2 in 1962 in its voyage to Venus. There are also secondary questions that had to do with astrophysics and with planetary science. And the problem was you needed some way of getting out there. The notional spacecraft is in the little sketch. This was going to use a nuclear electric propulsion system, which of course everyone knew would exist by the year 2000. If you were sitting in 1977, it had a launch mass of 32 metric tons, and it needed a little over 20 metric tons of mercury for propellant. Well, again, the engineering didn't quite work out that way. They did also have a Pluto orbiter that they were going to send out as well to go by Pluto on the way out of the solar system. So, the science was there. The statement of the science questions indeed has evolved, though, and that's informed by the new information that we got back first from the pioneers, and then from the Voyagers and their enduring missions, and as well as getting the new information that we're getting now from New Horizons as it has passed by Pluto and is again starting to enter into the outer part of the solar wind. So we talked these days about our habitable astrosphere. So an astrosphere is a generalization of our own heliosphere to the other similar magnetic cocoons that we think envelop other stellar systems where there's exoplanets. And one of the questions is, well, okay, we see all these exoplanets now. We know that they exist, something we didn't know about before the 1990s. And their main sequence, their stars, they're on the main sequence. They'll also have stellar winds. A lot of them do, we know from various remote observations. And one of the questions is, well, what role does that play in the habitability of the system? And basically you have a supersonic wind blowing out. This is looking at the bottom of a sink with water spraying out from a faucet. And at some point you have another flow of material here, in this case the interstellar medium or water coming in from the left side. And then that sets up a bow shock, and it sets up a so-called heliopause in the real world that separates the matter of interstellar space from the matter of the solar wind. We look out, and we've actually, in the infrared, we can see a lot of structures around a lot of stars. A lot of the ones that are seen here, Mira, Zeta Ophiuchi, and the others, these are actually from very strong interactions from the main sequence, from the main stars in those systems with the local interstellar medium that they're embedded in. Our own astrosphere, our heliosphere, if it were being looked at from a long distance away, would not be so obvious. And indeed, if I think about the other kinds of astrospheres that might be of interest in terms of habitability, for something like a dwarf G-type star, such as the one that we're around, right now we'd be actually hard-pressed to see it. The thing that we do know is that our astrosphere is habitable, and we know that because we are here. So one of the questions of this, and again, looking back to the science, is, well, okay, so what are the processes that help to shape the heliosphere? And what we've been learning from the Voyagers is that it really is a new regime of space plasma physics. If I look at this interaction region from where that I've gone through with the Voyagers, the termination shock is something a bit different. Everybody had expected that the flow of the solar wind would go from supersonic to subsonic, and with a heated medium in the so-called heliosheath region, an intermediate area between the shock solar wind and the external interstellar medium. And that's not quite what we saw. So it turns out that within the so-called heliosheath, the solar wind is actually still supersonic, just not as much so. But the other thing that's happened is if I look in velocity space, that is the distribution of velocities, it was first really described by Maxwell in his papers in the mid-1800s. There are these non-Maxwellian particles, ions and electrons, that carry away a lot of momentum, a lot of energy, and just simply not be describable by something that we encounter on the face of the Earth, or can encounter here, because basically it's a plasma and it's all collisionless, and so there really is a new piece of physics that's afoot, and that's doing something about actually setting up this heliospheric boundary region, which we really don't understand. One of the things that we've attempted to do is to try to actually look out and try to look at what the shape might be of this overall interaction. So this is one of the models. This got the name of being the Poisson model for fairly obvious reasons, which is actually from a large numerical code that's been run on a supercomputer. There are as many different shapes as there are different models, I think, that people have done, because it's very, very tricky to try to come up with something that will actually match all of the approximations in physics that we know would be needed to give an accurate representation. We know that one of the issues is that with the magnetic field direction, because from Voyager 1 and Voyager 2 are both in very different hemispheres of the overall heliosphere. Voyager 1 to the north, Voyager 2 150 AU away from it to the south. And yet, as in crossing into the very local interstellar medium, there's not really that much of a change in the direction of the magnetic field, which makes no sense whatsoever in any of these models. And so that's one of the things that we're still trying to puzzle out. A lot of new results are continuing to come in from the Voyagers as we go out into the local interstellar medium, even though we were more than 30 astronomical units away from the heliosheath, this boundary. And obviously there are still some things we don't understand. One of the other things is really understanding to what extent that the heliosphere and this overall structure actually helps to shield us back at the Earth. This is a plot of galactic cosmic rays, and this is coming out to the heliopause, and you can see this little uptick here. And what you're looking at here is the level of galactic cosmic rays that are actually in nearby interstellar space. And you can see as that I come into the heliosphere, there's actually shielding that's going on, because these are energetic particles that are being shielded, being shielded out by the magnetic field that's associated with the sun. Of course, galactic cosmic rays were discovered by Hess back in 1912 in balloon flights over Austria. And at the time, everybody had wondered, well, what was the source of this radiation? And we don't know the exact nature of that. It's thought that a lot of people think that this is from supernovae events, for example, that are able to accelerate particles to really high energies. Again, certainly they come from the outside, and certainly they contribute to the background radiation level that we actually see here on the Earth, but they don't contribute as much as they would if there were no heliopause. So again, another interesting puzzle to work out. There are a lot of processes that shape the heliosphere. One of the things that we've learned how to do is to do remote energetic neutral atom imaging. Basically, what happens is I can have neutrals that are interacting with very, very fast charged particles. They undergo a charge exchange collision, and so now all of a sudden I have neutrals that are traveling very, very fast, and I have much lower energy charged particles that are entrained in the magnetic field. But I can now take an instrument a long way away and actually make effective pictures in these ENAs and be able to get an idea of mapping out what the three-dimensional structure really looks like of these very large, very far-flung plasma structures. And this is something that has been done with NASA's IBEX mission, which is in orbit around the Earth. That's been going on for quite a while now, and you can see this so-called ribbon structure. Again, these are ENA emissions, and this is from looking at stuff that is coming in from out and around the heliosphere. There's still some debate about exactly where the origin is of these particles. We've also got a similar kind of imager that was on the Cassini spacecraft. These are some of the ENA maps there. And actually, one of the interpretations of Cassini is, well, maybe that the heliosphere really is more spherical than like a windsock, which has sort of been the preferred idea here for quite a while. So if anything, these new measurements have actually not helped to define what the answers are, but rather shown us that things are a lot trickier than we had thought that they might be. We certainly know that the heliosphere is dynamic. The effects of the dynamic sun and with variations of shocks in the solar wind actually affect the dynamics and the energetic particle mix throughout the entire heliosphere. And one of the things that we're actually learning is that these effects actually propagate all the way through the heliosheath as well as into the nearby local interstellar medium from the Voyagers. And once upon a time, back before the Pioneers were launched, everybody had said, well, obviously, any sorts of perturbations like this should totally die out by the orbit of Saturn or so. Again, a nice theoretical construct, but it was one that was also simply wrong. And then finally, there's the question of the very local interstellar medium itself. We know something about the neutral clouds that are in our vicinity. We know that we are in the local interstellar cloud right now, the so-called LIC, and we know that we're near the edge, and we know that we're headed toward the G cloud, which contains the star system of Alpha Centauri. And exactly how that these various regimes cause differences on our own system, not really well understood, but on the other hand, the actual temperatures and pressures in these clouds is sufficiently different that there may have been very significant differences that have cropped up back during the ages that humans have been on this planet. So one of the things to do is to be able to actually get out and do direct sampling of the very local interstellar medium, and that could tell us about things all the way from recent nucleosynthesis, constraints on cosmology, give us an idea of the various Lick processes in history, and again, galactic chemical evolution. And without being there, you can't see any of this because all these materials that are pristine in the local interstellar medium are being swept around us by this heliosheath interaction that we have between our sun and the local interstellar medium itself. So there's an evolutionary journey to our heliosphere. We typically have gone around the galaxy several times now since its formation. Let's see if I can pick this up. So here we are. Here are the dinosaurs back here, and here's the dinosaur extinction, and here's the human race, and here's today. And so there have been on the order of about 20 times that we've actually gone around the Milky Way galaxy during all of this time. And one of the issues, of course, is, well, okay, so what's happened during all of that? Well, it turns out one of the things that's come out just recently is that people are finding some rare isotopes that are actually in sediments at the Earth, things that shouldn't be there. That looks like it tracks back to maybe something going on about 3 million years ago, and there's some evidence that at the time that the solar system itself may have been in a different cloud structure that had sufficient external pressure to actually get rid of most of the heliosphere and really push those boundaries down into very close to our planet. And the interesting thing is some of us have talked about and have noted is, well, okay, so 3 million years ago, give or take what? Well, we don't know because it's a big set of error bars. But that's also about the time that Australopithecus afarensis, one of the early hominid species, came to be on the planet as far as we know. So, one of the perhaps far-fetched, but perhaps not far-fetched questions is, is there a role that all of this has played in human evolution over the years and over the eons? We don't know, but we need to know something more about what the local interstellar medium looks like to even be able to speculate. So that's the science, but you've got to put together some sort of a formalized science statement. And this has taken a lot of work, and anybody that has worked on this sort of thing knows what a nightmare that it is. And if you haven't worked on it, you would think it's kind of like launching a rocket where you just count backwards from 10 to 0 and then push a button and the engines turn on, right? What could be so hard? So one of the things that we've done in the course of the study with a lot of these volunteers that we've had is to really try to put these questions together and really to formalize those in terms of 3 top-level questions about how the heliosphere is upheld by the physical processes from the sun, how does the sun's activity in the interstellar medium and possible inhomogeneities influence the dynamics and the evolution the global heliosphere. And yes, I'm reading off the monitor because I can't remember all of these off the top of my head. Sorry, guys. And also then, of course, how do the current local interstellar medium properties inform our understanding of the evolutionary path of our heliosphere? So this is sort of the restatement. These trace right back to the kinds of questions that JPL had in their report back in 1976, 1977, with somewhat different language. Here's the pretty pictures that go along with that. You should take a look at our executive summary that's got these sort of summarized. And again, kind of illustrating that there really are three phases that or three regions that you would like to explore. Basically go back and do the entire heliosphere, but quote unquote, do it right with modern instrumentation. There's a lot that we missed with the Voyagers because we simply did not know where to look, and we did not have sufficient sensitivity on the instruments that are flying on the Voyagers to be able to look at the plasma and the magnetic field. There's the issue of the heliosheath, this transition region going from the heliosphere proper into the local interstellar medium, which is thicker than people had thought. There are these energetic particles that were not exactly quite what the origin of the acceleration is, but certainly have a lot to do with, how that this interaction all takes place. And then, of course, out into nearby interstellar space itself and trying to understand how that all comes together and helps to inform us of what our own history has been. Now, there are other science goals one can think of, and again, the 1976-77 JPL study talked about exactly these same things. They talked about sending a probe out to Pluto. Well, we have now been to Pluto with New Horizons, and it was not just some ball of rock. I mean, it was a pretty spectacular encounter. We learned that Pluto is a world in and of itself out there with its large moon Charon and all the other smaller moons. But it's only one of many dwarf planet systems that are out there. One of the trajectories we looked at, could take you to Orcus and Vanth, which you probably have not heard of, but Orcus is another one of these small dwarf planets. It's actually about the size, I believe, of Charon at Pluto, and Vanth is its satellite, large satellite. And then there's Quaoar and Wewat. Again, two names that don't exactly roll off the tongue, but on the other hand, with the naming conventions of the IAU, they have been formalized, and another one of these dwarf planet systems out there. And all of these things appear to have their own personalities. And of course, again, we've only gone by Pluto and just sampled that one. Another issue is the circumsolar dust disk. Of course, we're actually inside of a very dusty environment. That's why that we can see the zodiacal light. And one has to get at least about 3 AU, preferably further away from the sun, for that dust background to die off and for us to actually be able to see what sort of infrared background radiation that there really is out there, and understand exactly how that the dust environment dies off. We now know about dusty rings that are around other exoplanet systems, and we really need to know more about our own system to know how to do those comparisons. And then finally, if I can do that, well, I can actually be able to fill in a piece of the extragalactic background light spectrum that is sorely missing and has been missing, simply because this is light that comes from the earliest formation of the galaxies, not so late after the Big Bang. And right now, I can't see into that part of the spectrum because that piece of it gets absorbed by the dust that we're embedded in. So again, appropriate instrumentation, appropriate thresholds. These are things that go all the way from planetary science to astrophysics that right now we can't do simply because of the location that we're currently in. So you also have to worry as you're moving out through the system about how the science informs the concept of operations, as it is called. So you have to start with a science traceability matrix. This is what I was talking about part of this exercise. This is where we started 4 years ago. Looks pretty simple. I've got 3 questions. I've got some objectives. I've got some mission requirements. So should be a piece of cake, no problem. Well, then you think about it a little bit more, and it gets a little more complicated. And so this, and no, I'm not going to read through all of this, but suffice it, and it gets worse. But suffice it to say, this is, as you start thinking about all of this and thinking these things through, these are the kinds of things as you think through these various mission phases that I've got to be able to build a spacecraft that can actually functionally do this type of thing, and so that we can actually make these kinds of measurements. And the question is, well, do I have to be spin stabilized? Do I have to be 3-axis stabilized? Which way do I need to be pointing? How do I need to mount my instruments? So these are all these are in the dirty little depths of the engineering details that one really has to think about to be able to see, can you really pull off the kinds of measurements that you need, that are needed to inform the science and to be able to give you some answers. And so from our 4 years study, basically, if you're putting together a science traceability matrix, you map from the goals to the objectives to the questions to the investigations to measurement requirements to mission phases, to the mission requirements, the analysis products, and then finally closure. That is, with respect to closure, have I been able to put together a package with things I can build with the technology I have in terms of both the instruments and the spacecraft to actually be able to substantially answer the questions that I have posed in a quantitative fashion, so that I can either confirm or reject hypotheses about what I think that I currently know about the situation out there. This was kind of the in-between point. So here's for the baseline goal. This is where we ended up, and yes, you can download it from the website with an appropriate magnifying glass and probably be able to read it. Suffice it to say, in the first column there really are still 3 questions, but this maps through all of the things that you would want to know. It maps through which instruments that you would need to have and which of the various phases of the mission that you would need to use them, and then some notion about what sort of data you would get back and whether that might be sufficient to close the questions. And again, there were about 80 people that came together doing all of this over a year-long period. And getting 80 scientists to all agree on something, for anybody that's tried to do that, is actually in itself almost a minor miracle. Well, this is the baseline goal about trying to do heliophysics. So one of the things that we did, we were being funded by the heliophysics division, and so our guideline was to think about, what could you do with a heliophysics-only mission? But then there were also these other augmented goals. So were there things that you could do about still doing the heliophysics and yet be able to address the astrophysics questions as well as the planetary science questions? And we're all scientists, so the answer, of course, is yes, and that's what that one looks like. So that was thought through as well. So we sort of had both of these flavors of what kind of science that you would want to do, or could want to do, or might want to do. And again, with the idea of really putting together a menu of the things that might be out there rather than being prescriptive of a distinct mission overall, because that's the sort of thing that, if this were to be picked on by the Solar and Space Physics Decadal Survey as something that should be gone ahead with, that NASA would usually put together a science and technology definition team to go back through all of this, really do a sanity check, and then be able to make some down selects from what is really a rather large menu of things. So now the heavy lifting, which is where we did a lot of the work, really, was to integrate the science with the engineering of mission implementation. So this is the other side. So you need to start with some sort of a set of engineering requirements, which we did. We needed to facilitate closure on this. So we imposed a technology horizon to address what's been referred to as incessant obsolescence. This always comes up when you're talking about an interstellar probe. Well, obviously, somebody's going to be able to invent warp drive if I wait for a century, so why do you want to do this now? And, my counter to that is, well, do you have an iPhone? If the answer is yes, well, why did you go ahead and buy it? You could probably wait for another 10 years and you'll have a much better one. Think, grumble, grumble. Well, the point is that the way that we make progress is we keep trying to move ahead bit by bit, and always pushing the envelope. And the trouble is, if you stop, you never can stand still. You can either go forward or you can slip backward. And in thinking about it, we've of course been trying to get the Artemis mission off, and there have been a lot of holdups. But if you think about it, no one has built a space vehicle that's that large since the last Saturn V was launched back in 1972. And if you're not doing these things all the time, you tend to forget some of the knowledge. And so that's one of the reasons for going ahead with this. So we said, well, you had to be able to launch no later than the 1st of January 2030, because that puts a stick in the ground about how long that you can wait before that you're going to have to do something. For downlink, a lot of these missions have talked about operating out to 1,000 astronomical units, and so we said, okay, we're not going to say anything about how far we can necessarily get or how fast. We're going to design the communication system to be appropriate from 1,000 AU and then see where that takes us. For power usage, we said, okay, 600 watts when I start the mission. That's what you can get from 2 of the GPHS RTGs that were of the same kind that are powering New Horizons now, and the 3 that powered Cassini, and the 2 that powered Galileo, and the 1 that powered Ulysses. I know how to build these things. I haven't built them in a long time, but I do know how to build them, and I know that they can be built. And I know that after 50 years, they'll decay to about half the power output. So that gives me a line in the sand for how much power that I might have available at the end of the mission of 50 years. And again, that feeds into longevity. To try to actually design something to last for 50 years and convince a review panel when you're trying to launch it that you can really do that. And this is a little tricky because, right, normally if you said, well, I'm going to design something that's going to last for 5 years, well, I could put something in a thermal vacuum chamber for 10 years and then, you know, it's obvious. Well, I'm not going to build a full spacecraft and put it in a thermal vacuum chamber for a century in order to prove it'll last for 50 years. So this is a different way of thinking about things if I'm going to try to do this. And we set this up so that these are independent of each other. And you can really think about having a box that the downlink's on one side, the longevity's on another, and the power's on the other. And suppose I have to have this, whatever I'm building, by the 1st of January 2030, it's got to be ready to launch. And then the question is, okay, what I want to do is to estimate the inclusivity of the implied compelling science and how much of that and how large a piece of that box can that fill up in order to try to make the case or not of whether that I really have something that is compelling to do subject to these constraints. Now, the central technical question has always been propulsion. Again, this is something I mentioned about the JPL study with the nuclear electric propulsion system. And the near future capabilities have always been the defining backdrop for the requirements. And we wanted to try to get away from that because what you really want to do is to unite the compelling science with engineering and technical reality. And so from that, we don't want to do that. That's probably not a good engineering starting place, right? So what we wanted to do was we really ended up picking on ballistic means of doing this. Now, this is how we split up the study. This is the initial schedule, where we started out really looking at science, the concept of operations, and simultaneously we put together groups looking at longevity, the instruments, the trajectory in the launch vehicle, the communications and the guidance and control trades. We looked at a heat shield because one of the ideas was to actually go close to the sun and do a so-called O-berth or powered gravity assist maneuver near the sun. But nobody had really looked at the engineering constraints of really going close to the sun and seeing what that was going to take. So we wanted to go back and visit that given our previous experience with building the thermal shield for Parker's Solar Probe, which would be inadequate for this, but on the other hand, that thermal shield was based upon basic research that had been finished about the year 2004. We wanted to see what else had come along since then. You have to put together an overall consistent mechanical design. You need the power system. I mentioned a little bit about that. Then you got to put everything together in the box and stir it around and really come up with a system that is consistent. That's not that easy to do. And if you think it is, well, you need to try it sometime. We put together an interim report based on that. We had a series of 4 workshops for the community, and this came out. What we did is we were doing this every year. We were briefing this out to the science and engineering community and to NASA about where that we were. We ended up going ahead and rewriting the report several times and revising it, and then came out with the final report, and that final report is what's published out on the web. So there are 3 different mission concepts, and again, nothing new to this. People had talked about this in 1976, 77. You can always do better if you do a Jupiter gravity assist. It makes a big difference. I can pick up about 3 AU per year of speed by going around Jupiter rather closely. Another option is to actually keep a rocket engine with me and fire that at my closest approach to Jupiter. We wanted to take a look at that trade. People had talked about it, but it had never been really quantified. And then the third one was this so-called Oberth maneuver. So Hermann Oberth had posed this question in 1929 about what's the fastest way you could get out of the solar system with this limited amount of fuel. And he concluded that, well, I go very close to the sun and then I do a rocket burn there. But no one has ever taken a look at, again, what you'd need to do for the heat shield. So again, we laid all of these things out. We've got publications throughout the technical literature, some in conference proceedings, some in actually peer-reviewed journals. In looking at the spacecraft reliability and longevity, we looked at how you would do the modeling. We looked back at the historical record of how long things have lasted. We looked at a lot of the physics of failures techniques that are now entered into a lot of the systems engineering to see how that you would apply those. We actually took a look at the design we came up with on this and estimated that we probably had something like a 93% chance of being able to last for 50 years with the design, subject to the way that we put the pieces together. Again, the power decrease is pretty close to the historical silicon germanium converter RTGs. Again, these are the ones that have flown on the Voyagers, the MHW multi-100-watt RTGs for 45 years now, and then the longest lasting GPHS RTG is 16 years to date on New Horizons. And the chart off to the left just gives you an idea of what some of the degradation rates in power look like. Plutonium-238, that's the key element in all of this, or the key isotope, has a half-life of around 83 years. That's the blue line toward the top. You can see that the power falls off faster on all of these various units, and that actually has to do with a degradation mechanism because of running the thermal converters hot for these many, many decades of time. And gradually we've gotten better and better. There's probably some room for improvement, although NASA has literally thrown several hundreds of millions of dollars at trying to solve that problem over the last 30 years without a lot of advances. It's a tough problem. It's a materials problem with all sorts of issues. So, but the fact of the matter is that we do at least know how to build something that would suffice for the sort of mission designed here. We have looked at what's called the next-gen RTG. These are a new set of RTGs that are being developed by the Department of Energy right now. This is some of the modeling that we did, and it looks like with the, this is somewhat smaller than we would actually want to fly. This is with a so-called 16-block GPHS RTG starting out with a design life of about 224 watts at the beginning, and would be down to zero power in about 73 years and would still have power remaining after 50. So you can't keep these things running for an infinite amount of time, but on the other hand, 50 years is probably not totally crazy. So in using this, we put together mechanical layouts for options 1 and 2 for the passive Jupiter assist and the powered Jupiter assist, in which case you got to make some changes for having the acceleration at Jupiter due to that extra stage firing, and some issues with respect to the plasma wave antennas. It's something everybody wants to fly. You can't deploy really long ones like you can if you go ahead and burn all the rocket engines at the Earth. We also looked at this solar Oberth maneuver, and this gives you an idea of the kind of heat shield design we came up with. And basically what happens is you need to build a heat shield that is large enough with enough structures to be able to radiate the heat back and to be able to shield the kick stage rocket engine. This is a solid rocket engine because this is what we know how to do. And that ends up with here, for example, a 900 kilogram spacecraft, but about 1,600 kilograms worth of thermal shield. And so it turns out when that you put all the trades together, this actually does not trade that well about giving you much of an increase over what you can get with simply burning all the stages back at the Earth. The material that we used in making these estimates, there's a new kind of it's a new kind of metal carbide layer where this is done by a small company up in Idaho Falls that are really at the top of their game in this. What they were able to do is to take carbon fiber, which has a very high vapor pressure limits when you get it up to above 3,000 degrees Kelvin, and at the same time be able to put several tens of microns worth of things like hafnium carbide at the surface in order to give the strength to keep the outgassing from causing the fiber to fall apart. So it's a way of being able to keep the mass down while keeping the thermal properties up. And this is actually what we used as a design point for putting together those notional thermal shields. And again, even with this, which is kind of out there at the edge of technology right now, it's not sufficient to actually make the trade a good one. And we actually went through, we looked at various designs with 3 different kick stages, separate designs for perihelia of 2 through 6 solar radii at 1 solar radii increments in order to really span this and to really do an overall comprehensive trade to see how that things would work out. We ended up also doing an initial power estimate, again, looking back at what sort of amounts of power would be needed by various pieces of the spacecraft, including the payload, the spacecraft with the avionics, with the communications system, and so on. Compared those with what's been actually implemented on New Horizons, the Van Allen probes and Parker Solar Probe, as sort of a sanity check in all of this. Looked at how when we put the spacecraft together with basically with a dual string mode where there's a backup system for everything. Again, pretty standard practice these days. We looked at the telecommunications trade space. How do you get a decent signal back from 1,000 AU? Well, you can start out with the DSN, but at some point, if you're going to try to keep the power or the communication system coming back, you're going to need something like the next generation VLA or the square kilometer array, things that are on the horizon for radio telescopes. And we've talked to some of those people, and you could indeed use these as a means of actually getting data back. Now, one of the things that we did come up with is to use X-band. We're asked, well, why don't you use Ka band or why don't you use optical comm? We looked at those, and the problem is I don't have a way of being able to actually point the spacecraft that well from very, very large distances after very, very long times of operation. Because on the spacecraft where we use Ka band, we've got reaction wheels. They tend to be heavy. They tend to need a lot of power, and I'm losing power as I go out in time. So that's a trade that doesn't work out. And the way to really build in the reliability is you need to go back to X-band. And this is actually the reason that X-band was used for the Voyagers. It was the same problem. They didn't have a way of providing the extra power with time as you're going out from the solar system with reaction wheels, because those take a lot of power. And again, this all ties back to the amount of power that is available. We looked at about 160 bits per second as being a minimum from 1,000 AU, because that's what the Voyagers are giving us right now. We know we can do a good science case with that. We also looked at the case of what if one of the RTGs fails, and I've got 2 of those. And then again, there are trades where that you keep some of the instruments working and you turn some of the others off. Realistic cost estimation. Well, we took a look at this as well. We did a lot of work with the various databases that are out there. We had our people at APL who have worked on cost estimates both for Parker and for how the things have worked out on Parker, as well as these other missions, just to try to come up with some realistic prices. And I can tell you, I think I've got it on a summary. Basically, we came up with a phase E cost that is going to be very large, because if you're talking about doing science across 50 years, that's a lot of money. It's not something that you would usually usually cost for. I mean, the James Webb Space Telescope, I think, is currently funded for only 1 year of operations, and it's going to last a lot longer than that, or there's going to be another set of problems. The space vehicle, the spacecraft itself, we estimated a cost in FY25 of about $1.7 billion. And that's actually pretty comparable with what was done on Parker. However, that does not include the price of the launch vehicle and the radioisotope power supply. Those move a lot, and basically what one has to do to get reliable numbers is to wait until you get closer to the time that you're actually flying something. So the synthesis is putting all of this together. Now that I've got a launch, and I got to put that together with the launch vehicle. And this is actually a movie from the SLS RS-25 Green Run hot fire test. This was in March of 2021. The engines for the SLS work. I was hoping I was going to have a movie showing the launch of Artemis 1, but obviously that hasn't quite worked out with the timing, although I understand that they're now looking at September the 23rd as a next attempt to fly. All of the upper stages that we looked at are solid stages that are either in production or almost in production in order to try to put something together, again, that would be ready to launch by 2030 and could also be certified for having nuclear power sources on board. We looked at the various shroud configurations and how all things would fit together to make sure we had something that would fit, because you can't go ahead and fly something that won't fit within the rocket. So this leads to this, again, this sort of integrated science payload and spacecraft configuration for these two different versions of the mission. We put together a model baseline payload. This is the final. We actually looked at the placement of all the instruments that you would need in order to have appropriate fields of view. This is for heliophysics only. This is what we came up with for the augmented payload. Dr. Alice Kokoris, who's here as one of the guests tonight, is one of the people that was very instrumental in pulling all of this stuff together. And again, a lot of detail, again, a menu, the sort of thing that is out there that could be considered. Here's our baseline mission. Basically, we were looking at something that could launch into the forward part of the heliosphere going into the region of space from the incoming interstellar wind. Takes you out to needing to launch probably sometime after 2036 with a Jupiter gravity assist. About 860 kilograms for the spacecraft, including the payload being at about 80 kilograms, very comparable to the payload and the spacecraft mass for the Voyagers, it turns out. And again, I've got the cost here. Phase Z, about $230 million for a decade of science, with an aim point of 5 decades of work. And again, with this technology horizon in place. With an escape speed from the solar system of about 7 AU per year, so better than the 1960 report estimates, almost twice that currently of Voyager 1, the fastest moving thing to leave the solar system, which is moving out at 3.6 AU per year. We actually looked through at a variety, putting all of this together. We looked at 181 different cases of launch vehicles. There's only 112 of those that actually closed. The other ones ended up being too heavy to fly. And from those, we were able to select one that was the fastest time out to about 375 AU in 50 years. And that was what we used on the baseline, that has a Centaur upper stage and a Star 48BV solid fourth stage on the stack. The launch opportunities happen once every 13 months. That's the synodic period between Earth and Jupiter. And we map those out on the sky. The places that are in red are where that you would like to launch. Again, fly-out speeds everywhere from 7 to about 8 AU per year. The so-called ibex ribbon of the energetic neutral atoms is marked out in violet down on the bottom of part of this figure. And again, we actually went back and looked back at what sort of opportunities we would have for flybys of small KBOs during each one of these little islands. Again, something that a future team would need to pick. And again, looking at what you could do and what you couldn't do with trajectories. So again, really trying to adopt this menu model rather than be prescriptive of one particular point design. And then sort of the other summary of the baseline mission characteristics, talking about, this really would be for 5 generations of leaders. We would really do this by design, and a decade's about a solar cycle. So 5 generations, 5 solar cycles to go from the Earth out into the nearby interstellar medium, and really to solve some fundamental new questions. And again, this is sort of where we ended up with looking at the various data rates over the time periods involved. There's also international activity. Some of our colleagues in Europe put together a proposal called Stella for being able to have some additional instruments that could fly on this from Europe. That was not accepted for funding because there is no Interstellar Probe mission that is approved in the United States, but nonetheless, it served its purpose to really get the people on the European side of the pond to be thinking about what at ESA might be something that could be done in the future. And a lot of this was described at the COSPAR meeting that took place in Athens this past July. So that was the long version. Here's the short version. And I'm going to be quiet and let you just watch. I'll be sort of quiet. Again, you have to start, I'm not going to be that quiet. You're going to have to start with the ideas, right? So how can you do ideas these days? Well, you need a whiteboard, right? And then once you do that, well, of course, then you can build something. And then you have to launch it. And this is a sketch of an SLS Block 2 cargo vehicle. And again, the nominal baseline would be for a launch in 2036. This is pretty much the same launch sequence it'll be going through by Artemis 1. The solids coming off, going up on the RS-25s. After all of the stages have been used, we would go ahead for the heliophysics version, extend these 50-meter long wire antennas, and we'd be on our way to Jupiter after crossing lunar orbit in about 6 hours after launch. So an opportunity for doing Jupiter science on our way of picking up another 3 AU per year. So this Jupiter flyby actually picks up something like 40% of the total flyout speed we can have. Here's Orcus and Vanth. Not a targeted flyby, but seen from afar. And again, we could do some things with taking a look at those, even if we didn't go as close as we did with New Horizons to Pluto. And of course, the key is getting away from the sun, continuing to be taking these measurements as we go, and finally getting out to the point where that we can start putting together the models that we've now got on grids, along with actual measurements in the interstellar medium and in the outer heliosphere, and seeing how those would mesh together and help to inform us of what this bubble home that we have in space really looks like, and as a stepping stone to be thinking further and further afield, going out to the neutral gas clouds that are even further out, but we would at least have the innermost boundary conditions. And then, of course, you need some more probes later on that can go faster, and that's going to be somebody else's problem to solve all the problems that I've talked about, and out into our corner of the Milky Way. And again, like it or not, this is part of what our home looks like. And again, we've been around the center black hole for quite a few times now. And we're not quite sure what we have and have not been exposed to, but and how that's affected us here at home on the Earth. But certainly something that we could take a look at. We think that we've done a pretty good job with the engineering report, and we think that this is something that, if we've made the case, that is something that actually NASA could think about doing. And basically, exploration is always a human endeavor. And it all comes back to all of us here back on the planet, regardless of where we go out into space. And as a very short teaser, Well, before I do that, here's what a possible future could look like. We actually looked at a timeline. Let's suppose this goes forward. You'd put together a science and technology definition team, and yes, this is basically this is the same kind of timeline with various reviews that was undergone by Parker Solar Probe, and we could get a launch around 2036, and that could take us out to something on the order of 400 AU. In the late 2080s into the early 2090s. And just to give you an idea, in the year 2113, if I got the number right, that's when Pluto's at aphelion. So, and we went by with New Horizons about the time Pluto was at perihelion. And now for the teaser. So in the meantime, what we don't know can kill us, and APL is working on that problem, and so I want to draw your attention to 17 days and counting to the DART impact. That's on the 26th of September 2022, and so stay tuned. That'll be a near real-time seeing if we can protect the Earth from asteroids. And so thank you very much for your time and your attention.
Thank you so much, Ralph. Just the beginning. So we have time for questions. Joe Schulman. Oh, sorry.
A member. Is this on? Do you hear me? Yeah, there you go. I'm a member and a past president of the Philosophical Society. And my question was, you talked about faster than the
I can't.
faster than sound, but there's no sound in space, so I didn't understand that.
Oh, well, okay, a good question. So we still talk about speeds in plasmas as being supersonic and subsonic based upon what the plasma temperature is and about how fast that it is flowing. And this gets back to Maxwell's description of the so-called Maxwellian description of particles and gases. So certainly, you know, the air in this room is all collisional, but nonetheless, if you were able to actually count in some small volume what the speed of all of the particles were, you would get a distribution of speeds that would look like a Gaussian shape, and the mean of the average of all that would be the speed. You really wouldn't notice that too much unless you're out on a windy day, and then the width of that distribution would be indicative of the temperature of the gas in the room. So if I go out into the near vacuum of space, but not quite total vacuum, where that I have a plasma, I can do the same thing in terms of doing the accounting, but now with the various plasma analyzers, energetic particle analyzers, where we can actually see that velocity distribution and be able to figure out what the effective temperature is and what the effective speed is, and I can ratio those two, and that tells me whether it's supersonic or subsonic. With the caveat, and it has to do with how fast how fast the disturbances actually can propagate. So, for example, in a supersonic plasma, I end up having shocks because I can't be able to propagate the information back to, you know, from the impediment that I've got in the flow back to being upstream. So it's the same kind of principle, but you're right. It's taking it over to collisionless plasmas, but the concepts are still the same, it turns out.
Please stand up, tell us your name, and if you're a member.
Hi, my name is Charles Yarbrough. I'm a guest. It was a really interesting talk. I was going to ask, what made Voyager so durable and able to live and keep broadcasting for so long? I understand that's still in like reasonably good operating condition. I mean, despite being out there for 40 plus years.
Yep, we're at 45 years on Voyager 1 as of the 5th of September, so we just passed that anniversary, and it relied on three different things. It relied upon, if you look back at my chart, it relied on the technology. Basically, when they were designing Voyager, they said, look, we're going to design this for 4.5 years, because at the time, trying to design a spacecraft, this was against the backdrop of doing the grand tour of the solar system, which was realized you could get all the planets out to Neptune in 12 years by doing gravity assist. And they said, you know, we have no idea how to do that. So The original price tag that was given for doing it was about $1 billion, when $1 billion was a lot of money. And so the budget was cut back to $300 million, with the idea of being able to go out to Jupiter and Saturn. So the idea was that you tried to figure out how to last for 4.5 years. You flew 2 spacecraft. That's why there's a Voyager 1 and a Voyager 2, for one thing, because you didn't always have that reliable of a spacecraft. You didn't know how to do that. And you also worried about having a very particular parts program where that you did qualification of all the electronics parts. And then you got lucky, which is another part of all of this, because, if you look back, Mariner 2 went to Venus. Mariner 1 was going to go to Venus, except for range safety, had to blow it up before it hit Titusville, Florida. Mariner 4 went to Mars. Mariner 3 was going to go to Mars until the shroud didn't deploy off of the upper vehicle. Mariner 9 went to Mars. Mariner 8 was supposed to go, and I don't remember where it was lost. But you kind of get the picture. I mean, going back into those early years, the track record was not necessarily so good for being able to know how to build things correctly. Practice makes perfect. We've gotten better as we have built more spacecraft, and that has really had a lot to do with it. And then you also have to have somebody that will keep funding it. I'm on the Voyager science team. I know of at least 3 occasions where the attempt was made to turn the Voyagers off. The first one was in 1983, before Voyager 2 got to Uranus, because the claim was, well, you've actually succeeded in all of your scientific goals. You went to Saturn, you went by Titan. That was the 4.5 years. So we should just turn it off and save the money and spend it for someplace else. And of course, there was hue and cry. There was back and forth, and eventually, what I would consider to be clearer heads prevailed, and we're still being funded now, and we're looking for ways of actually extending the lifetime of the Voyagers, hopefully to the 50th anniversary, for at least another 5 years. And we are gradually having to turn off the heaters on board for some of the instruments. So far, they've been still working. We haven't frozen anything yet, and we haven't broken anything yet. But at some point, we're going to have to start turning off some of the other instruments in order to keep some of the instruments still going for as long as possible. So it's still an unfolding story, and we'll see. But it's not an easy thing to do, and we've actually within this study, we've talked about the fact that probably the most difficult thing with respect to the longevity is not going to be designing something that will last for 50 years, but convincing a review board that we know how to build something that will last for 50 years. Because if you can't do that, you're not going to get the money in order to do it. So it's a bit of a catch-22 situation that nobody's really run into before. So that would be some new ground for us.
I want to take a question from Zoom, Carl Merrill. Carl, can you mute your mic and ask your question? Hopefully this will work.
Thank you, Larry. Talk. I have basically 2 questions. One was Freeman Dyson had suggested using nuclear explosions for the Orion, and you didn't mention any of that, so I wondered why that was abandoned. That's the first thing. And then the second thing is that we already know quite a bit about the fact that the solar system is in a large bubble, a local bubble, based on astronomical studies of the temperatures of the gases, et cetera. And I wondered, how does this mission complement what we're learning from these other methods of studying X-rays and ultraviolet emissions from those gases?
Okay, well, if I can address the Orion concept first, you're right. I mean, that was actually, in talking to Freeman not too many years before he died, there was some question about him having come up with that idea, and he said, yeah, that was not a very smart thing to have thought about. But at the time at least, it looked like a good idea. That was actually inspired by the Operation Plumbob atomic test, where that there was some evidence that a manhole-sized steel cover on over a nuclear explosion out in Nevada got launched into space at something like 60 kilometers per second, about 5 times Earth escape. That was one frame of a very, very, very fast movie film, and that was really what inspired these guys to try to do it. Ultimately, programmatically, what killed the program was the atmospheric test ban treaty in 1963. Dyson actually wrote about that because at the time they had estimated that, well, every time they launched one of these things, which is going to include something on the order of 100 atomic bombs in order to get their 10,000-ton spaceship into orbit, that the release of radiation be something like about 10% of what was being released in the Pacific theater by the U.S. and French nuclear tests that were going on. And they said, well, that's not that big of an addition, so I'm sure nobody will get in our way of that. But with the test ban treaty of 1963, of course, everything changed as we've learned a little bit more. And it was a little trickier than that. There was actually I think it was Project Hot Rod. I think you can find the film on the web. That was the use of 7 TNT charges of trying to build it was a 1-meter diameter pusher plate, was flown off the coast of La Jolla, California. This was all done out at what's now General Atomic, was the center of this. So it was a little hard to do compared to what they thought that they could do with the beginning, and it just ended up not being practical, and then all the politics came in as well. With respect to the local cloud, you're right. I mean, what you've described is sort of the broad brushed outlines of what we currently do know about the local cloud, but the real question is, well, okay, so was this local cloud, for example, the product of one or multiple supernova explosions? Well, if you're going to try to answer that question, you really need to be able to get out there and really need to see what the isotopic composition is. One of the real issues is, well, okay, so how far are we out of thermal equilibrium, because that tells me something else about the electron recombination time and how long that it might have been in the past that these events happened. That would be informed by looking to see if there's a superthermal particle population in the electrons, which some people have talked about. So you're right. There are these very broad brush things that we know, but it's a little bit like going out to the coast and saying, gee, there's an ocean out there between us and Europe, and it's filled with salt water. Which is all true, but if you would really like to know more about the ocean currents and really would like to know about, how that's affecting weather and other things, you really need to be able to take more detailed measurements, which is, of course, the thing that we have done over the years with most vehicles that have actually crossed the ocean. And so this is a case of trying to dig deeper, and by digging deeper, you learn more, and by learning more, you usually end up uncovering new mysteries and asking new questions. So that's at least part of the motivation.
I'm Tim Thomas. I am a member of the Society. I would like to ask you about the possibilities of actual interstellar transportation or movement. I know you've given a lot of thought to getting to the heliosphere, and I'm very impressed with how difficult it is and how long it's going to take, considering how actually near it is when you look at the galaxy. So what is your opinion or thoughts about what we might do in the long run to get further?
It's a tough question, and I keep quoting from the Hitchhiker's Guide to the Galaxy. Space is big; it's really big, and that's the problem. I mean, if and of course part of this is, well, the Voyager's it's Interstellar Probe. I mean, we're going to get up to a fast enough speed that we can get to Alpha Centauri in 20,000 years. What's your hurry? So it's partially it's a question of trying to do it, quote unquote, say within a human lifetime, and it just so happens that was actually That was actually a motivation for a science fair project that I did when I was 16 years old, because I had the same question, because I used to inhale science fiction novels all the time. And of course, you know, you could write about, everybody wrote about star travel, so what could be so hard? And it's one of the things I discovered was the work that Eugene Sanger, who had worked on the work with von Braun actually he'd worked with the Luftwaffe in Germany on the America bomber, but that was a different story. And then he worked with von Braun in the U.S. after the war. And he was the one that coined the idea of a photon rocket, because he had looked at this idea of, okay, so what are the ultimate limits to rocketry? How fast could I really go? And he said, well, if I take, a little naive, if I take matter and antimatter and I put them together, I get photons. And if I get photons, I've got an exhaust velocity of the speed of light. Of course, I need to collimate them. That can be a little hard to do with 511 keV photons. But anyway, I could think about doing that. And so the question is, well, what would it take in order to actually do a round trip? And so there were some works that had actually been done by Sebastian von Horner back in the 60s. Carl Sagan did one of the works as well, looking at relativistic rocket mechanics and what would happen if you could get to really high speeds and how did that translate. Sort of the bottom line is that you could think about if you could build a rocket and if you could continuously accelerate it at 1G, so I don't have to worry about weightlessness, that's an easy one. And let's say I want to go to Alpha Centauri. And so the numbers work out something like I accelerate at 1G, and then I turn around at halfway point, and I decelerate at 1G, and then suppose I just turn around and I repeat that and come back. So it turns out I can do the round trip in about 8 years, ship time, which is about 12 years Earth time, because at the midway points I'm at 95% of light velocity. Looks reasonable until I start looking at, well, okay, so how much power does that require? And so the estimate I put together, and this is actually on the web at an APL website, although it's sort of a stealthy place that I've stuck it, was you can do the calculation. I think I assumed that I had a human module with a crew of a couple of people. You know, God only knows. I was in high school at the time. What can I say? And that weighed about, I think it was 100 metric tons. Okay, so if you do that and you made some allowances for the fuel tanks, I came up with you needed about 1.5 billion tons of hydrogen and 1.5 billion tons of antihydrogen. And somehow I need to put those together at an appropriate rate, and then I could do it. Well, of course, that's the problem. I mean, and there have been a lot of science fiction novels that people have written, and the problem is just that you're fighting with physics in terms of trying to get things up to really, really high speeds. You could, of course, back that off and say, well, what if I do something in 100 years? I can maybe build a spacecraft that might last for 100 years. I've told people that if you look at the Earth, the oldest running mechanism that we have actually built is the Oxford Bell. It's also sometimes called the Oxford Buzzer. It's in the basement of the physics building, one of the physics buildings, or the physics building at Oxford University. It's a pendulum, and it swings back and forth. It's 10 centimeters long. I think it's about a centimeter in diameter for the pendulum between two electrodes. There's a battery and then repel it and attract it. There's a battery of unknown composition that was sealed up in molten sulfur when this thing was put working, and apparently was put into motion in something like about 1840, and it's been running ever since. And so that's the longest running thing that we've ever had. It's undergone a few billion oscillations, I think, if you do the calculations. So maybe you can build things. Maybe you can build a spacecraft that would last for 200 years. Maybe you could build one that lasts for 300 years. You could use americium-243. It's got a half-life of 7,000 years. Can I build electronics that would last for centuries? Well, not today. Could you eventually? Well, maybe. Of course, that doesn't solve the problem of actually getting a person on board unless you just ship their DNA back and forth. But and you could think about doing that too, I guess. But maybe there are some things like that that are out there, but we're going to have to do a lot more work first.
Did you win the science fair?
Well, actually, I didn't. I got some of the special awards. Part of the problem was that I was interviewed by an engineer from General Dynamics at the time. It's Lockmart. This is in Fort Worth, Texas. And he asked me, well, what's the specific impulse for this rocket engine? And I told him, oh, about a year. And he was like, well, you know, that makes no sense. This kid doesn't know what he's talking about. Well, of course, it turns out if I've got an exhaust velocity the speed of light, it really is about 97% of a year. So the answer was right, but nobody believed me. Oh, well.
We have a question from YouTube. Colin Alberts asks, are you locked into launching with SLS Block 2? Wouldn't all your configurations fit nicely on a Starship or super heavy?
Okay, that's a very good question, and we've looked at that. Basically, this has to do with the answer has to do with the information that we've had available, because we have been interested in what you could do with, say, a 3-stage New Glenn from Blue Origin, or with a Starship Super Heavy from SpaceX. What ended up happening was that we made some initial inquiries and didn't really they weren't terribly interested. In the meantime, we had been working with colleagues down at Marshall Space Flight Center out of one of the SLS offices, who were very interested in knowing, well, you know, being able to support something about looking at what you could do with science on an SLS. And quite frankly, this whole idea of using a large booster goes back to a National Academy study that was done in 2008. And the question was, can you do any science with an Ares 5, which was the baseline at the time for the Constellation Moon program, which was subsequently canceled and then sort of reborn like a phoenix as SLS Artemis. So the issue has really been that we'd certainly be interested in taking a look at that. We have engaged some of the people at Blue Origin and SpaceX on a few different occasions, and we've gotten a little bit more information. But we're still sort of at the point of trying to get enough information for really doing some comparisons. Right now, we're under some non-disclosure agreements, and so it's really not something that I can discuss in terms of extra detail on those. But we certainly haven't ruled those or anything else out that's kind of got that sort of a capability to it.
Okay, Bob, blue microphone.
I'm Bob Hershey. I'm a member. What are the main lessons from the Voyager missions that will help on the Interstellar Probe?
So it's a good question, and you know, I think one of the things that I think one of the reasons that we thought about, you know, what you really need to do is to do a mission by design that's going to last for 50 years. And while you're doing that, you really should build in this idea of having this turnover of about once a decade, because this is something that Voyager did not do. You also have to be careful about hanging on to blueprints and specifications. There have been some issues with Voyager where none of the drawings exist anymore, for example, because it wasn't going to last that long. So this is taking up space. So we ought to throw this stuff out. Bad idea, you know, given what we're trying to do now. So I think that one of the big things is to, you know, plan for a long-term success from the very beginning. Of course, there's some people that don't like to hear that, because now you're spending money on science operations and you're not spending it on, you know, the engineering on building the next mission. But if you really want to do something like this, that's part of it. Part of it is, I think, having a really, really good parts program, again, in terms of looking at the qualification of parts and being able to do the appropriate testing on the parts to really test for things that are going to work. Certainly having a dual string system is something that is going to be absolutely absolutely needed. You're not going to do this with a single string system. And basically, you know, again, getting everybody on the team to really be thinking in this very different mindset of what you're trying to do is something that really is fundamentally different from what we've ever done before. But if we want to turn into a truly spacefaring species, which a lot of people like to claim that we want to do, I think these are some of the things that we need to be thinking very, very hard about and thinking about how to actually do them. So it's probably more things on the human side than on the technical side that we have really learned, with the exception of don't throw the old specifications away.
Casey, last question. One more.
Casey List, Johns Hopkins University Applied Physics Lab. So Ralph,
Member?
And a member. Ralph, you mentioned more than once that very reasonably, why don't we wait another 100 years until we get a better propulsion technology? I'd like to point is that we've already waited 60 years, some years, since the Simpson Commission and since this idea was first proposed. And that you may not have mentioned it, have already looked into things like solar sail propulsion or laser-assisted Earth propulsion and other techniques that seem to be possibly close to the horizon, but don't seem to work and don't close. So I'd just like you, if you could comment on that. In other words, it looks like the time is now to go and launch this using the biggest chemical rocket we have.
Okay, Casey scared me for a minute. Casey's part of our team, but he can throw me curves sometimes. No, I think that those are all, well, as we have discussed before, those are all very good points. And yeah, I think you just hit about 3 more lectures that I could give, but we don't have the time for that now. I think you're right. I mean, I've said to people, for example, think about the Wright brothers. Suppose it's 1903 in December, and you're wandering out to Kill Devil Hills, and there's a couple of bicycle mechanics, and they've got this really weird looking glider, and they're trying to do something with it, and you go over and you say, well, what are you guys up to? And well, you're trying to build a heavier than air machine. Well, why do you want to do that now? It's not going to really be able to perform very well. If you waited a few decades and looked at, what you could do about taking, say, a couple of hundred people from New York to London in maybe 6 hours tops, this is what you're doing now is a waste of time. And if you'd have talked them into going back to their bicycle shop in Ohio, we might never have had airplanes, right? Because again, it's the funny thing about technology. Again, I think it's very clear, and this is some of the stuff that Vannevar Bush talked about in his book that came out in the report to Roosevelt and later to Truman at the end of World War II about science basically being an endless frontier, that you can't stand still. You can move forward, or if you don't move forward, you will move backward. And if you move backward, things can get very bad. I've told people, well, at least in the West, we've run that experiment before. It was called the Dark Ages, and it didn't work out too well for a lot of people. So, I think it's a question of, you're right, that, and this whole incessant obsolescence thing, again, this is part of the moving forward. And we have always, one of the things that's been a major strength of the United States since the post-World War II world has been our capabilities in doing research and development, which has led to a lot of things. And you can't always, it's like the quote from Einstein about if we knew what we were doing, it wouldn't be called research. And you learn a lot by trying to do things that people just have never done before. And this is going to try to go to a place that people have never done before. And again, it's within reach. And sure, we can wait a while. I mean, this whole idea, of course, comes from a short story by A.E. Van Vogt, who was a science fiction writer. It was a story called Far Centaurus. I believe he originally published it in 1944 in Astounding Stories, if I remember correctly. And it was about the first manned, of course, it was all men back in 1944. Sorry, everybody else. But the first manned expedition to Alpha Centauri. And so with a great deal of fanfare, the think there's 3 or 4 guys. They set off for Alpha Centauri, and they get there, and they're welcomed by the brass band, and the flags flying, and they're like, this is after 500 years of suspended animation, of course, and they're like, we're very confused, and they're like, oh, well, we've named everything for you because you were the first people to leave, but it was 100 years after you left that the first expedition actually got here, and that's when we were able to colonize the system. And so, of course, not being satisfied with that, they ended up they wanted to go back home. Somebody figured out how to dump them into a white hole, and they went back in time with the technology that allowed you to get to Alpha Centauri in a short period of time. So then it turns into a time travel story and a time paradox. But I think that's probably the earliest mention of that. But again, this idea of something being called incessant obsolescence, it's come up over and over again. There's actually papers entitled Incessant Obsolescence in some journals, which means, of course, that it's got to be a legitimate thing to talk about, right? So you have to keep pushing the envelope, and this is one of the envelopes that I think is worth pushing. The Voyagers are going to go offline. Right now, we have had something headed toward the outer heliosphere since the launch of Pioneer 10 in March of 1972, and if we don't do something about replenishing the Voyagers, that corner of the so-called heliospheric science observatory, and we don't start doing it now, all of a sudden there is going to be a huge vacuum for many decades to come. So, yeah, I agree with you, Casey. I think you've got a good point.
I think we're going to wrap it up. I apologize for people who haven't had a chance to ask their questions, but there is a social hour and there are some refreshments in the back, and maybe you'll be able to ask your question then. But we're almost at 10 o'clock, and it's time to wrap it up. So, before you go, Ralph, I want to give you a small token of thanks. It's a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, signed by me on behalf of all of the members. And you can learn a lot about why they started the Philosophical Society. But in a nutshell, it was to be the Royal Society of Washington, D.C.
Very good. Well, thank you so much.
Thank you.
Thank you for the invitation to come tonight.
It was our pleasure and our honor. And before you go, a few closing remarks. The next meeting will be the 2,463rd meeting on September 23rd, 2 weeks from today. The speaker will be Bindu Nair. She is the Director of Basic Research at the Department of Defense, and she will be speaking on the endless frontier and funding basic research in the United States. So she'll give you a little, I don't exactly know what this talk will be like, but I will tell you what the motivation was. I have a colleague at the University of California, San Diego, and he got an award from DOD, the Vannevar Bush Award. It's a funding mechanism. And they give out like 5 of these a year or every so often. And they are unrestricted research funding for a period of years. And this is pretty rare. You don't go through peer reviews or anything like that. They pick you because they like the area you're in, and they think it may have some relevance in the long run to the mission of the DoD. So I got very interested in this because my little way, like to advocate for basic research and funding people who are curious and get in the lab and have a lot of capability as scientists and let them figure out what's worth studying. So I was very curious about this program. And I got in touch with the head of the program, and the head of the program said, no, you should really have the person who doles out all of DoD's basic research funding. And so that's why we're having this person come and speak. But just out of curiosity, how many of you know that DoD has a basic research funding mechanism worth about $3 billion a year? Oh, a fair number. Smarter than, well, of course you know. Yeah. Okay. Anyway, she'll be coming to speak, and I hope you'll show up because I think it'll be interesting to meet her, talk to her, and learn about the perspective of the DoD on funding basic research. So with that, please check the PSW website for updates. We'll be posting additional speakers hopefully in the near future. www.pswscience.org. And before we go, let's thank all the people who actually worked to make tonight's program work. So. So thank you, Ann and James and Robin and Brett and Jared and Robert and Lloyd and Bill Mitchell, who actually hasn't done his part yet, but he will be over the weekend. And one last item, please return your name badges to the plastic bins in the back of the room. And with that, I will adjourn the 2,462nd meeting of the Society. I wish everyone a good evening, afternoon, or night, wherever you happen to be. The meeting is adjourned.